So I'm sure you have heard some wonderful talks over the last 2 days, right? You have heard about like a synthetic organic chemistry, you have heard some talks on quantum chemistry, you have heard some talks on probably this morning atmospheric chemistry, and then now you have heard about heterogeneous catalysis and all those things, right? So if you see of all this, like if you look at, I think there was a talk on physical organic chemistry. So if you have seen that you're all first year chemistry students, and you have seen that chemistry is kind of a central subject which can diverse into various areas, right? One is into material applications, one is into your quantum computing, right? You can have this, but I'm sure you must not have heard it here in the last 2 days, where how chemistry is being extremely useful in understanding the biomolecules, like understanding the physical principles of biomolecules, and it has a very huge applications in drug discovery. Okay, so in the next half an hour, because I only have time till 12:50, so next 30 minutes, so I'll tell you something about basics of biophysical chemistry, what it is, what are the kind of problems that the field is addressing, and what are the tools that it is addressing, and in after lunch, post lunch, which is 2 o'clock, I'll slightly talk about some of my current research interests and what are the various projects that are going on, so that we can talk a little more in detail. So, how many of you have a course on biophysical chemistry in your MSc level? Not many, right? So unfortunately, that is because this is actually a highly interdisciplinary field. So only if you look at some of the top colleges in India, right? So if you look at, depending on the region, so there is a specialized version of this course which is called biophysical chemistry, where you are trying to understand the biomolecules by physical chemistry principles. Now, how many of you have studied something about biomolecules? So how many of you know what is nucleic acid, how many of you know what are proteins, and how many of you know what are carbohydrates and these kind of things? You all know this, right? So we will see like what is the physical chemistry, what advantage these physical chemistry principles are giving you in understanding that. Okay, as you can see this, so basically biophysical chemistry is a new area, or it's a relatively new area. It has been there for about a couple of decades. For some reason it hasn't picked up in this part of world, but it is a very established area where you apply the principles of physical instrument, basically physical chemistry, and you use the chemical properties to understand the biomolecules. So basically it's an interdisciplinary area. Like for example, your material science, right? Material science is also an interdisciplinary area. Similar to that, biophysical chemistry is also an interdisciplinary area where your main aim is to understand the biomolecules and their properties using the physical chemistry principles or the chemical principles. Okay, so now to put it in a simple way, it is something like this. So you have these large biological systems like proteins or DNA and other things, and although they look like biological systems, you know the structures. All of them are nothing but your chemical moieties. What are nucleic acids? What are nucleic? You know what is DNA, what is RNA? What are nucleic acids? So basically it's a nucleotides that are kind of linked to your phosphodiester bonds, right? And then you have a sugar attached to it. So although they look like large molecules, they are nothing but your chemical molecules, right? So at the end of the day, all the principles are governed by the chemistry behind it. And what are proteins? Proteins are amino acids, but they are much more complex. If you just take few amino acids, they have a simple structure, but proteins undergo a much more larger conformations and form a functional moiety. Now, one thing that I want to emphasize is, don't think that biomolecules means it has something to do with biology. Biomolecules are nothing but the chemical molecules that are important for the biological systems. At the end of the day, these are still chemical molecules, but these are very essential for running of your any biological system, right? So if you look at the properties, right? So if you want to understand these biological molecules, so what do you want to understand? So for any of these biological molecules, if you want to understand their thermodynamic properties, right, or if you want to understand the structural properties, or if you want to understand the kinetic properties, or there is a mechanical properties. So if you want to understand any of the physical properties, you use the tools of biophysical chemistry, and the methods could be experimental methods, they could be computational methods, or they could be theoretical. So you can approach, these are all properties, right? Structural property, kinetic property, thermodynamic property, and then mechanical property. So all these are properties, and for addressing this, you can use experimental tools, computational tools, tools or theoretical tools. So basically for you to understand like a simple biologist would only understand why it is happening. So the basic difference between a chemist and biologist in my opinion is biologists would try to understand what is happening. They are only interested, okay, you are seeing a color change, you are seeing a functional change. So what is happening is what they are interested in. Whereas as chemists, because we have information on the molecular property, we are interested in how it is happening and why it is happening. So if a biophysical chemist would try to understand the questions of why and how. So how it is happening and why it is happening, right? So okay. Now let us see what kind of properties will. Again to tell you, so if you take a simple DNA, right, which is a nucleic acid. So although we all write it as this nucleic acid, as this structure, what is it? Although we are writing it, this is nothing but there is a sugar that is connected by, there is a ribose sugar that is connected by a phosphodiester bond, and then you have, in addition to that, every sugar is connected to a different bases, right? Whether it's a, G, C, T, depending on that you have your, so again DNA would have a deoxyribose, RNA would not have a deoxy, that means it will have both OH, whereas a DNA would have only a single OH. So although we write it as this, so I am going to show something as this, but this is nothing but the chemical structure is going to be conserved like this, right? Now if you look at a protein, so although we are writing a protein like this, what is this? Protein is nothing but it is a linear chain of polypeptides, right? It is basically amino acid chains that are joined by a peptide bond, right? So it is basically a peptide bond that goes on to form a protein. We will talk about it in a bit, and these proteins can again combine. These are called structures, these are called tertiary structures, and they combine and form what are called quaternary structures, which are basically your enzymes, right? So okay, how many of you are aware of, how many of you know, so what was chemistry Nobel Prize awarded for in 2024? So you are all first year MSc students, right? Drug discovery, computational tools, drug discovery, okay. Protein, okay, I am hearing good words, but I am trying to combine them, yes. Drug discovery, computational tools, protein, and what was it exactly awarded for? mRNA was a couple of years back, not this year. Yeah. Okay, so basically it was awarded for, I'll tell you in a brief. So if you look at this linear polypeptide, right? So I'll just show you this. Now you have a linear polypeptide chain. You have a linear polypeptide chain that actually takes a, because these are peptide bonds, right, that actually takes a secondary structure by formation of the hydrogen bonding, intramolecular hydrogen bonding. These could be either alpha helices or beta sheets, and these secondary structures further fold further and form what is called tertiary structure of the protein, and which forms quaternary structure, which is this. So it is such a simple thing, right? But for the last, I would say 80 years or so, we know that, or much more than that, the proteins are there. Proteins are nothing but you have a polypeptide bonds that fold into secondary structures, that fold into tertiary structures, that fold into quaternary structures. But if I give you a sequence of amino acids, you all know there are 20 essential amino acids. If I give you suppose 100 amino acids of different, made of these 20 amino acids, you cannot predict what structure it is going to take. So if you give us, if a simple organic molecule, if you take a molecule, you know what is the structure and how does it assemble, right? But a simple 20 amino acids, you only have 20 amino acids, and if I give you 20 amino acids, so I give 100 amino acids, of which there are only 20 different amino acids, right? I give 100 amino acids, and if I give you 20 different amino acids in that, you cannot predict how the structure folds. And people have been trying to crack this nut because this is a very, very important thing. So I'll come to that, but predicting the structure of the protein is very, very difficult. So this year's Nobel Prize was given to, it's called AlphaFold, and there is another called Rosetta. These two are computational algorithms which can predict the structure of proteins if you give them the sequence. So you can understand how difficult it was and how important it is that for just predicting the structure of the protein. That means if I give the structure, if I say, okay, there is lysine, leucine, you know amino acids, right? Lysine, leucine, some glycine, if I give some 100 amino acids, how does it fold? So for predicting that, so it folds into this, and you see this is not a cartoon, this is nothing but basically there is a alpha helix and then there is a beta sheet and it forms a quaternary structure, right? So for predicting this, this was given a Nobel Prize this year. And this was all done by chemists, okay. So the molecules are biological molecules, but understanding the system or predicting this is nothing but chemical principles, trying to understand the energy minimization process and trying to understand the homology. So that was what kind of resulted in this. So you can understand, now you might say, so why is it, okay, the problem is difficult, I'll tell you why the problem is difficult, but why should we even know the structure of proteins? Why do you think we should know the structure of proteins?
Predict how to bind in the biological system, so or this drug, how to bind in the DNA and the protein linkages.
Right.
So
no, that's very good. So basically, many of the drug targets, now you name any disease, right? About a large proportion of the diseases, the targets are proteins. That means you are inhibiting the action of that protein, right? For example, now you must have seen the like 5 years back COVID, right? So people have said like, okay, there is a ACE2 receptor and there is a spike protein. A spike protein comes and binds to ACE2 receptor. Spike protein from the virus comes and binds to ACE2 receptor. So these two are proteins only. Now how will you develop a drug? You have to develop a drug that will break these interactions, right? For that, what you should know how the structure of these two proteins. Only then you can break the So breaking means you are not going to heat it, right? If you are going to heat it, all the proteins will die. You have to specifically break this particular bond. And how do you do that? You need to know the structure of the protein and you have to develop a small molecule that will inhibit this. And by the way, all these are only understood if you understand the chemistry behind this, right? So if you look at this structure and function of protein, as I said, protein folding is a very, very complex process that even today it is considered as one of the hot topics, in the sense, why does a protein, how does a protein fold? Can I just give you a sequence and do that? And now we kind of cracked it by computational tools, which is called homology modeling, okay. So this is how your works. So as I said, proteins, why should we know the protein structure? Because proteins are very, very important, in the sense, if you take hormones, if you take enzymes, like if you take the structural support, for example, your heart, your muscles, all those things are basically built by proteins, right? Then you have ion pumps. So you know that the entire heart is nothing but it has channels and ion pumps. There are ions going in and out. Those are all made of ions. And then you have antibodies, basically. So all these are proteins. So it is very, very important to understand the proteins, and for understanding the proteins, you need to understand the molecular behavior of those things. So that is where your biophysical chemistry comes. So biophysical chemistry tries to understand the thermodynamics. So if you are looking at thermodynamic properties, it is going to give you like free energy of binding, the affinity of binding, right? And then stability, mechanical stability, right? If you're basically your muscle is expanding, contracting, or if your hand is moving, right? All these are basically, the proteins are the ones that are kind of undergoing doing this process. So you need to understand the stability of that. And then if you want to understand the structure of the proteins, you use spectroscopy tools. For example, for understanding the structure of the protein, the most common method, the most advanced method now is electron microscopy. But before that, you either used X-ray diffraction or NMR spectroscopy, okay, to understand the tertiary structure of the proteins. But if you want to understand the secondary structure of the proteins, you use UV visible spectroscopy or circular dichroism spectroscopy. So how many of you know what is circular dichroism spectroscopy? Or how many of you know UV visible? UV visible, you know. So, okay, so when you have a chiral molecules, right, when your system is chiral, there is something called differential absorption, because your light is polarized light, right? So you have a circularly polarized light. So because the light is polarized, you will have a differential absorption. The right one will absorb differently, then the left one will absorb differently. So circular dichroism is nothing but differential absorption. So that will give you secondary and tertiary structures of the proteins. Okay, now kinetics. Right. So if you understand the kinetics, it is going to tell you about the rates of processes, various processes and other things. So the first thing that I am going to talk about it, how is biophysical chemistry an important tool for drug discovery. But before that, what is the information that we are going to get from the biophysical properties? Okay. So these are various properties that you can get from understanding. So if you want to understand the protein ligand interaction, now as I said, protein is nothing but an amino acid, it is a biomolecule, and then you have a small ligand. If you want to understand the interaction, interaction means what will you determine? If you want to determine the interaction between a protein and ligand, what properties will you determine? So how can I say a ligand is binding to the protein or not? What property will you be able to, what property should you measure to determine whether a protein is binding to ligand or not? No, that is the interactions governing. But if I give you a protein, if I give you a ligand, I'll say do some experiment and tell me whether this ligand is binding to the protein or not. How will I do that? Okay, computationally. Okay, what does docking give you? Donating property of the. It is not universal because most of these are non-covalent interactions. So some of them are electrostatic, but most of these interactions are non-covalent. So many of the protein ligand interactions are governed by hydrogen bonding. So you really don't need an electron acceptor and electron donor. Most of them are governed by hydrogen bonding interactions or hydrophobic interactions. Okay, so if docking is a computational method. Now I want to understand if I give you a protein, if I give you some organic molecule, and I want to see this organic molecule is binding to the protein or not. What properties will you measure? Don't go to computational law, but only experimental. What do you think you will be using? So what happens if a molecule binds to other molecule? What happens? What happens if a molecule binds to other molecule? There will be change in what? There will be change in the molecular mass, but and what else it will be? Bond length will not change. These are all, as I said, these are small. Again, I give you an example. This is the protein molecule, large protein molecule, and these are small organic molecules. These are, like I gave you the names of it. They are going to bind in some place, right? So they are going to bind in some place. Now how will I determine? So there are few methods. One thing is, whenever there is an interaction, non-covalent or covalent interaction, whenever there is an interaction, there is a release of energy or absorption of energy, right? But these are all energy related. So you can measure the change in energies, right? And what else can you measure? So you must have heard of lock and key model of ligand binding or something. So whenever a ligand binds to a protein, there is a change in the structure. So you can determine the structure of the protein, right? Before and after binding, right? And what can you see? When somebody said size of the protein changes, but you need to have a very, very sensitive tool because this is a very, very small molecule compared to this. So even if this is binding to that, the size change will be very minimal. Okay, it will not be huge change, but still you can determine what is called as change. So just to give you, so protein ligand interactions can be measured by heat changes, structural changes, and some property changes, mass, and changing binding energy is what I said. Okay. Now let us see. So let us see how do you measure the change in energies. What method? You're all physical chemists, right? So you know how to measure, or you're all chemists. At some point you have studied. All of you have studied chemistry, right? Or all of you are studying chemistry. Now, how do you measure energy changes? What apparatus will you use? This is actually you must have studied in school also. What is the method or what is the instrument that you would use to determine the change in energies? Calorimeter or calorimetry. This technique is called calorimetry. So you use what is called as isothermal calorimetry to determine the changes in the energies. Okay. Now, as I told, the second point was structure, right? Now, if you want to determine the changes in the structure, what are the techniques that you can use? Structure changes. I think a few minutes back I have told you what are the methods that are used to change the structures. You can use NMR. If you want to look at the tertiary structure changes, you can use NMR. You all know what is NMR, right? NMR, and then IR will not change much because what does IR give you? But are there any changes in the functional groups here? And other thing is, IR is good. It is, people use it, but if you have, all of them in the protein are peptide bonds. right? Although the alpha peptide bond in the alpha helical and beta sheet are slightly different, but all of them are peptide. There is only very limited functional groups. In proteins, do not have a large number of functional groups like this, not like ethers, esters and all those things, right? Mostly it's peptide bond or CH bond or CN bond, only these are there. And even if a new molecule comes, the changes will be very less, but it's not a very sensitive technique, so people do not use much of the IR. The major thing is NMR and mass spectrometry can give you change in the mass but not change in the structure. One of the most other common one is, so if you are looking at a material, so how many of you have taken a course on solid state chemistry or something? If you have to look at the structures of crystals, what do you use? XRD. So crystals will give you, X-ray diffraction will give you a change in structure, and more importantly and more recently, I don't know if you have been there, so in the entire I would say in India there are 5 or 6 centers which can do what is called cryo-electron microscopy, and IIT Madras has one. So cryo-electron microscopy. So do you know what is cryo-electron microscopy? You know what is electron microscopy? What is electron microscopy? You determine the densities of the atoms in that, right? And what is cryo-electron microscopy? Low temperature. So at a very low temperature, so basically you will do a structure of the protein, that is called cryo-electron microscopy. Okay. Now these are commonly used tools for determining the protein ligand interactions, or basically if you want to understand the changes in the protein ligand interactions. Now coming to the kind of questions that you can address, as I said, you can use these biophysical tools to understand protein ligand interactions, structure and dynamics of proteins. Okay, structure and dynamics of enzymes. Do you know what is the difference between protein and enzyme? What is the major difference between proteins and enzymes? Enzymes are defined by their ability to catalyze a biochemical reaction, right? Enzymes are defined by their ability to catalyze a biochemical reaction, just like you are. So these are other like your heterogeneous catalysis or other things. So these are enzyme catalysis, basically where they are able to catalyze a specific reaction. Now, they could be just proteins or proteins with other biomolecules. Then you can determine what are called protein-protein interactions. So I have given you one example, right? Where these are proteins, right? This is one protein, spike protein, ACE2. This is just an example of COVID I just made. So this ACE2 is the receptor in your body, and this spike protein is nothing but it is there on the viral shell. Basically, whatever virus you were talking about, coronavirus, right? That the shell has a protein. So it is not like it will just come inside, right? It needs to have interaction. So this particular spike protein will interact with the ACE2. This receptor is there in our body. The blue one is in our body. This green one is coming from the virus. Once the virus comes and sits there, these two interact. Although when we are saying like this, so this is the interacting region. If you see the interacting region, you see there are specific amino acids like phenylalanine, leucine, lysine, arginine, then you have aspartic acid and other things, right? So you have basically certain amino acids that are interacting. When you are saying interaction, it is not like a glue, it will just stick there, right? These are nothing but chemical interactions. So you can determine what is called as protein-protein interactions. And as I said, why is this important? So only if you know the interactions, then only you can break these interactions. So how do you prevent the entry of a virus into our body? You prevent the entry of virus into our body. Suppose okay, now if I give you this challenge, right? So we know that this is the structure of the protein and these are the interactions. Now how do you develop a drug to break these interactions? How do you develop? Now, like at the end of the day, our aim is in this to use the biophysical principles to develop the drug, right? So what is our aim? We know now we have, so one part of it is to solve the structure. Okay, I have used the methods that I just showed, X-ray, NMR, cryo-EM, and I finally solved the structure of the protein and I know what are the exact amino acids that are binding. Okay, now I want to break this interaction. So what will you do? How will you develop a drug so that will break this interaction? Drug similar to the protein in our body. Okay, then okay, huh? Hydrophilic interactions, okay. How do you know that target is better acting or not? So now you have developed a few systems of molecules. You all are very well aware of various organic backbones, right? Now you have developed various organic molecules. You do a docking and see which one is binding, right? But you are whatever you are developing as a drug, that should break this. Break this means what? The interaction with the drug molecule and the blue one should be stronger than the interaction between the blue one and the green one, right? Only then. So what physical property, what physical chemistry property will you use to see which whether this interaction is stronger or that interaction is stronger? What is the parameter that you will tell which interaction is stronger? So I have A, B are interacting, AC are interacting. Now how will I tell whether AB is a stronger one or AC is a stronger one? Then these are non-covalent interactions, okay? A is interacting non-covalently with B, A is interacting non-covalently with C. Now I gave you this. Now I am asking you to find out whether AB is a stronger interaction or AC is a stronger interaction, right? What is the parameter that you will determine for non-covalent interaction? Like if I give you this question, so what value do you need to tell which one is a stronger one? These are not covalent bonds. If I give a covalent bonds, I will say, okay, you give me the bond energy, whichever has the higher bond energy will be stronger. But these are clear, as I keep on saying, all the biological interactions that we talk about mostly are non-covalent and they are guided by hydrogen bonding or hydrophobic interactions. And some of them are electrostatic. So for non-covalent interactions, what is the parameter that you need? Exactly, affinity. So what is the constant that you have to determine? Affinity is determined by which constant? Have you heard of dissociation constant? No? How is it defined? If A goes to B, A plus B goes to AB, how do you define dissociation constant? Okay, A plus B goes to AB is the reaction, non-covalent. How will determine, what is the equation for dissociation constant?
So K is equal to a product divided by
concentration of? But if A plus B goes to AB, this is association or dissociation? So if I do a concentration reactant by concentration of the product, that will give me association constant, and reverse will give me dissociation constant. So this is all chemistry. So now you have developed a drug molecule, but how will you know that it will act? You will know if it will act only if you know the physical value. If you have to determine the KD of the drug with the blue one, which is basically a certain amino acids, and then you have to determine the KD of this interaction, and so you have to optimize the process so that you get a value or you get a molecule which has a better KD, so that can only replace this, right? That is how physical chemistry principles are useful in determining the, you just don't, like, it is not like, okay, one day I wake up and say, okay, this is a drug molecule. How that doesn't happen, right? If people do docking and all this. What do you mean by docking? Docking is nothing but you are calculating the free energy, right? So if you are calculating the free energy, the lower the free energy, the stronger is the bond. If you want to do it experimentally, you do what is called as, you determine, all these drugs are called, you determine dissociation constants, and then you actually calculate, develop a drug, okay. Now, as I said, biophysical chemistry, the protein-protein interactions can be determined. You can determine the process of protein aggregation. So how many of you know what is protein aggregation? So do you all know that there are structures, there are proteins, right? Proteins have what? A primary structure, a secondary structure, and a tertiary structure. Now these tertiary structures sometimes misfold, and then if they misfold, so I'll talk about it, just remind me, but when they misfold, they form what is called aggregates, and these aggregates are one of the major reason for a lot of neurological diseases. Have you heard of diseases called Alzheimer's? Have you heard of diseases like Parkinson's? So all these are caused because there is a protein aggregation. Basically, there is, for example, Alzheimer's, there is a protein called amyloid beta. We all have it, but as the age progresses, it starts to misfold, and once it misfolds, all these proteins come and aggregate, and that forms what is called as plaques. So in your brain you have plaques, and that results in Alzheimer's. Now when I say aggregation, Again, as I said, all these are chemical interaction. One protein is interacting with other, it is nothing but a kind of chemical interaction, right? So if you have to break these aggregates, you need to understand what is the chemical interactions that is governing them. And so that is what, so if you can understand what is called as protein aggregation process. And in addition to nucleic acid and protein, you can also look at nucleic acid protein. And I'll just tell you, you can also understand the process of, I started with this, so you can understand the process of protein folding. So what I want to emphasize is, all these physical chemistry principles or chemical principles, I don't want to just say physical chemistry, organic chemistry, chemical principles are used to understand the process of biological systems, and that is how you basically either develop a drug or understand a process. Okay, I'll now quickly move on to, okay, this one. So this is how the protein folding, as I told you, you have a linear polypeptide chain. So this is nothing but a linear polypeptide chain that folds into a nice, very nice conformation. This is called a folded protein, and this is called protein aggregation. Now you have some native protein, again this is a folded protein. There is a native protein, and under some certain stress factors means either there is a huge free radical generation or something, the structure of the protein changes. So once the structure of the protein changes, it oligomerizes and it forms protofibrils and amyloid fibrils, and these become fibrils in your body, and those will result in these diseases. So most of the neurological diseases, as I keep saying, Alzheimer's, Parkinson's, all these are because there is a lot of protein aggregation. So to understand the kinetics of aggregation and to understand the molecular forces that are governing the aggregation, you need to understand the chemical principles behind that, and you use the biophysical tools for that. Now we will talk about one particular, again I think I already told you this one. So basically you do what is called computer aided drug design, which is if you want to look at a drug discovery, right, you do what is called computer aided drug design. That means you take a large number of some millions of molecules and you first identify a protein target, like where do you want to identify it. You need to first solve the structure of that, right, and then you have to do a docking. Docking means you determine the energy of the binding, and then you isolate, and then you determine few molecules, and after that you synthesize the molecule, which is your synthetic chemistry. So once you have identified the molecules, you do what is called synthesis of the molecules. For example, there is a drug X, which is basically you are synthesizing the molecule, and that after the synthesis of the molecule, now there is only one target protein that we are doing, but in the body there are multiple targets, right? So what you have to do is you have a drug target X, drug X, then you have to start binding it with this whatever is our target protein, and also the off target protein. Off target proteins is proteins that are not related to that disease, and if they are binding to that, that will cause side effects. So you have to do both the analysis and determine which one has a better KD or which one is not binding, and determine. That is how you actually do a simple screening of drugs. Okay, so for all this you do biophysical assays like ITC, enzyme activity assays, and other assays to determine this. Now let's move on to another interesting problem in physical chemistry, which is or an interesting problem which is basically protein folding. Now how many of you know what, again, so protein, the entire field of protein folding or the concept of protein folding has been given Nobel Prize at least 3 times now. Okay, you can understand so Christian Anfinsen, initial one. So what he determined was, if you take any polymer, right, if you take a simple polyvinyl chloride or some other polymer and you leave it, it will never form a ordered structure. It will have its structure, it will not form an ordered structure, right? But what people have observed is, when you take a unfolded protein, any number of times you unfold it, you can unfold by urea or heating or anything. So you have a folded protein, and then you unfold it any number of times, and then you remove this denaturing. That means so suppose you have a folded protein, you give urea to it. What does urea do? Urea will break the hydrogen bond, so your protein will get unfolded. Now you remove the urea, the protein folds back. Okay, the same thing, you have a folded protein, you give a high temperature, it will unfold, and then you reduce the temperature, it will again fold back. What people have observed is, every time the protein folds back to the exactly same structure. Okay, this was observed very long back. Okay, so every time a protein folds back to exactly same structure, that means there must be some molecular interactions that are governing the folding of this protein. So this is called as Anfinsen's experiment. This is a very, very interesting experiment where he showed that proteins, when you do that, so it actually folds back to that. Then there was a question by Levinthal. Okay, So now if you have, suppose let us take, if it is basically forming back to the same structure every time, okay. Now let us take a simple example. A total, if I take most of the amino acids are, most of the proteins are very, very large. But let us take a simple example of a protein which has 100 amino acids. Now 100 amino acids, so 100 amino acids means how many bonds would be there? 100 amino acids. Backbones, how many backbones will be there? Backbones. So there is a C double bond O, NH, and then there is basically C double, then there is a carbon, and then there are other side chains, right? So each of them can have 3 different conformations. Like there are 3 different bonds between individual peptides, right? So if you can see 3 different bonds, and if each of those 3 conformations, so each of the amino acid can take 3 different conformations. If you do a simple permutation and combination, for 100 amino acids, how many different conformations are possible? 3 per 100, right? If there are 100 amino acids and there are 3 different conformations that each of them can take, each amino acid can take, then if you take the total number of conformations, that is, it is approximately 3 to the power of 100 conformations. So if you have a 3 to the power of 100 conformations, the fastest, like if you look at the bonds, right? If you arrangement of the bonds, how fast can a bond arrange? What is the time scale in which a bond will arrange? So what kind of motion does determines the arrangement of the bond? Vibrational. Okay, vibrational motion determines the arrangement of the bond. So what is the time scale of general vibrational motion? It is in picoseconds. Okay, 10 power minus 12, approximately it is 10 power. So I just give it as 10 power minus. So if there are 100 amino acids and each one of them can have 3 conformations, then there is 3 to the power of 100 bonds that can rotate. There is 3 to the power of 100 different conformations that are possible, and each conformation takes around 10 power minus 13. It would take 10 to the power of 27 years for a protein to fold if it is going by a random pathway. But a protein folds in microseconds or milliseconds. That means a protein will not actually go through a random search, but there is a molecular interaction that is governing it, and that is called as protein folding funnel. Okay, so you have an unfolded protein which can be there in any of them, but there are basically interactions that are governing the protein to go into this folded protein. So it actually accelerates the entire process. It is exactly reverse to what your energy barrier would look like. So you have an unfolded protein and it accelerates the folding into the native state, and sometimes you can have what is called as intermediates, but it's basically, so when you have a protein that is unfolded, it can accelerate, and there should be some molecular interactions. It will not be a random search, but there will be a clear molecular interactions that govern that and fold into the protein. Now, as I keep saying, so determining these interactions was the challenge, and that we could crack it only very recently. So what are the interactions that are governing this entire process of folding the protein? It's 12:55, so we will stop here and break for lunch, and then after lunch at 2 o'clock we will continue this.